All right, so yeah, thanks again for joining us on day 2. There's a few more that came in. If you could please change your Wi-Fi to Jilla Science. So stay off the other one we gave you yesterday for technical reasons. And the only announcement I have this morning before we start is that tonight is the problem session. It will be at 7:30 p.m. And it will not be in this building. It will be in the mathematics building. And of course, you can just Google mathematics building, but I drew you a little map. And the thing to do is just to go in through this entrance, okay? Because the building might be locked, but I'll be there to open the door for people. All right, so that's it for the announcements for the morning. So our next speaker is Daniel Spiegel, who will continue with his lecture series, and today he's going to talk about quasi-equivalence of states.
You shouldn't go off. Sorry.
Oh, scratch that. Daniel will just keep talking.
Okay. So sorry I forgot to update my titles, but I'm going to be talking about dynamics some more. Bob already introduced dynamics for us. I remind you that the dynamics in the C-star algebraic framework are given by a one-parameter family of automorphisms of the C-star algebra. So we have a C-star algebra is a C-star algebra. And we're going to notate aught. A is the set of bijective star homomorphisms from A to itself. And the dynamics is a strongly continuous homomorphism, group homomorphism, tau from the real numbers to the automorphism group. So in other words, the fact that it's a homomorphism means that tau s plus t is tau s composed with tau t. And the fact that it's strongly continuous means that the map from T into the C-star algebra, tau T of A, is continuous for all A in the C-star algebra. OK. And right now, what I'm going to be saying is it applies for any C-star algebra, not just the quasi-local algebra. OK? Good. So we have observables, we have states, we have dynamics. And once you define all those things in your Quantum 101 course, the thing is to start finding eigenstates and eigenvalues of the Hamiltonian. So we can ask, what is a ground state? What is an invariant state in the C-star algebraic framework? And this is a non-trivial question because right now there's no Hamiltonian. We do have an interaction, but the interaction is a bunch of little pieces. And when you sum them together, you don't get a well-defined object in the quasi-local algebra. So there's no Hamiltonian right now. So we need to think a little bit differently about what a ground state should be. OK. So certainly, if I'm going to have, if omega is to be a ground state, so if a state omega is to be a ground state, we have an interaction, and we have this one-parameter family. But that one-parameter family was not generated by a single Hamiltonian. It was generated by a bunch of local Hamiltonians. So I don't know who asked the question, but OK. Yeah, so we have a bunch of local Hamiltonians, and finding the ground state of one may not be the same as finding the ground state of another. So it's a slightly subtle question. OK. So right, if omega is to be a ground state, it should at least be invariant. So in the Schrodinger picture, a state omega will evolve to omega composed with tau t. That's how I evolve a state. And if this is to be a ground state, I should require that this is equal to omega for all t in R. OK. So already with that assumption, we can make a lot of progress. So let me assume that. And from there, we can descend to the GNS construction. So let h pi omega be the GNS construction, be the GNS representation. Of an invariant state omega. Then the conclusion is that there exists a unique, strongly continuous unitary representation. Strongly continuous unitary rep U from R into the unitary group of H, such that ut omega is equal to omega, and ut pi a ut star is equal to pi of tau t of a. So this is for all t. OK, and let me write this slightly more concisely. We can also write this as add ut composed with pi is equal to pi composed with tau t. OK, remember, just add is conjugation by this unitary. OK, this statement should remind you strongly of the uniqueness clause in the GNS representation. And that's exactly what we're going to use. So observe that omega of a is equal to omega tau t of a. And then by definition of the GNS representation, this is omega, capital Omega, pi of tau t of a omega. So that holds for all a in the C-star algebra and all t in the real numbers. So what you observe is that this state omega is represented by the representation pi composed with tau t. So omega is represented by the representation on H. The star homomorphism is pi composed with tau t, and the cyclic unit vector is omega. So therefore, by the uniqueness clause of the GNS representation, you get a unitary ut satisfying exactly these properties. OK, and now all we have to do is show that this is a strongly continuous unitary representation. So to show that it's a representation, observe that I could do add ut us composed with pi. That would be add ut composed with add us composed with pi. And I can just follow my nose. This is tau s. I can do it again. And this is tau t composed with tau s. And this is pi composed with tau t s plus t. And that's add u s plus t composed with pi. So by uniqueness, ut plus s equals us plus t, or ust, us ut. Okay. So it's a representation. let's show it strongly continuous. Maybe I'll erase this board. So for any a in the algebra, I have ut pi a omega. This is equal to pi tau t of a ut omega, but ut omega is omega. So this is pi of tau t of a omega. And this thing is continuous in t. So I've composed a continuous map with a bounded linear function. This is continuous in t. I did only put elements of the form pi a omega here, but those form a dense subset of the Hilbert space. And so you can make a density and continuity argument that this holds for all psi in the Hilbert space. That this is continuous for all psi in the Hilbert space. So t maps to pt psi is continuous for all psi in H by density and I leave you to fill in the details of that if you so choose. OK, so that's it. OK, so from an invariant state in our dynamics on the C-star algebra, we got a unitary representation on a Hilbert space, a strongly continuous unitary representation. And there's a wonderful theorem called Stone's theorem that gives you a Hamiltonian from this. And let me remind you of that theorem. So if T is a strongly continuous unitary rep, then there exists a unique self-adjoint, possibly unbounded. So we have to be careful when we have unbounded operators, but possibly unbounded this is an operator H from a dense subset D of H into the Hilbert space. So this is the domain, and it's a dense subspace. Such that ut is equal to e to the I t h for all t in R. And this dense subspace I can identify explicitly. So d of h is the set of all psi in H, such that ut psi is differentiable. At t equals 0. And if we have an element of the domain, then IH is the derivative. Let me write d by ds at us psi evaluated at s equals 0. OK? So this is wonderful. I now have a Hamiltonian, which is the thing I was missing. I don't want to erase that. I just did that. Oops. Thank you. The domain depends on the Hamiltonian, not the Hilbert space. Yeah.
Does the same theorem apply for group representations?
There's a similar theorem called the snag theorem, which I think is Stone, Naimark, Ambrose, and Gelfand. So you can put, instead of R, you can put well, for this theorem, you could put any topological group. And for this theorem, I think you can replace R by a locally compact group and get something similar. But I'm not 100% sure of every detail, so look it up yourself. OK? What? Oh, thank you. Thank you. Thank you. OK. So we have this ut, and omega is an invariant vector. So ut omega is constant, and therefore differentiable, and its derivative is 0. So omega is in d of h, and h omega is 0. OK. We were after ground states. So if this omega is supposed to be a ground state, there had better not be any eigenvalues of h below 0, because those would correspond to lower energy eigenstates. And we can take this as a definition. So let me say definition. Omega is a C-star algebraic ground state. If omega is invariant. We need the invariance just to construct the GNS. This thing is called the GNS Hamiltonian sometimes. So this is, well, if omega is invariant and the GNS Hamiltonian is a positive operator. Which means that its spectrum is contained in the non-negative real numbers, or equivalently, that it has positive expectation values for all states in its domain. OK, so this is fantastic. We've completed the dictionary for this entry. But it's slightly impractical. It's a little bit far removed from where we started. We started with an interaction, right? And then to get to this GNS Hamiltonian, we had to do the dynamics, and then we had to pass to the GNS representation and get this UT. And from the UT, we had to get H. So that's like 4 steps away from where we started. And if somehow you have an example that you want to compute, and you manage to construct this GNS representation and get a very tight handle on H, then by that time you'll be so tired that you can't check if this is positive or not. You'll have to take a nap. OK? So I think we need a better equivalent definition. Yeah. Yeah.
So it kind of looks like it's a local minimum of the energy, because you can't
Yeah.
lower the energy by applying quasi-local.
Yeah. Yeah, that's right.
How do you know you have a local ground state? Or does this definition include sort of maybe high energy states that are just in
So yes, it does, to answer your last question. And so if you have a bunch of these C-star algebraic ground states, yes, they're all sort of local ground states. And how do you tell which is a global ground state? Maybe you could try evaluating the ground state on the interaction. Or maybe it's not really, maybe it doesn't really make sense to compare the energy of two things that are in different superselection sectors. Not a, yeah. So. Okay. So I would like a little bit more of a direct approach to this. This is very beautiful, but it's also kind of indirect. So this GNS Hamiltonian was obtained as a derivation or derivative of this ut. A more direct approach will be to take a derivative of tau t, because that's where we started. So I'm going to define an operator, which we'll call delta. It'll be defined on some domain, which is a subset of the C-star algebra. And it'll take values in the C-star algebra. And it'll be defined in exactly the same way. So delta of A is equal to the derivative of the interaction now at s equals 0. And the domain is all A such that the derivative exists. OK. So this has some very nice properties that make it a nice algebraic object. So first of all, D of delta is a star subalgebra of A. And delta is a linear map. You can check this just from the definition of the derivative. You can check all these things just from the definition of the derivative. So delta is a linear map. These are easy properties to check. Delta satisfies a product rule. And delta plays nice with the star operation. And such an object has a name. It's called a symmetric derivation or a star derivation, or sometimes just a derivation. That's a good question. So for a time-dependent Hamiltonian, you can still do Lieb-Robinson bounds and still get some kind of dynamics in the thermodynamic limit. You won't have I'd have to think a little harder. I don't want to say something wrong. And maybe I should also say, you can do all of this for open quantum systems too, like Eric was talking about yesterday. But then again, it also gets a little harder. I'm trying to present the easiest case. OK. Some other properties. Another nice property is that if A is in the domain of delta, then tau t of A is in the domain of delta for all t. And the derivative on tau t of A, well, tau t and the the derivation commute. And this is equal to the derivative at time t of tau s of a. Okay, so that's another easy property to check just from the definition of the derivative. Okay, so we can definitely keep going. I have not yet told you how this relates to ground states. We can definitely keep going with the abstract theory. It will get a little more technical. And so in order to stay grounded, I want to go back to the quasi-local algebra and do this for the specific case of a bounded finite range interaction. So I'm not going to relate this to ground states yet today. Right now, it just looks like a good idea. Sorry, I will relate it to it today, but in my next lecture, which is also today. OK, so we'll just have to be patient and wait till after lunch to see how this relates to ground states. So I want to go to the quasi-local algebra. And I want to work with a bounded finite range interaction. This is the simplest case again. So I'll remind you what that is. So remember, an interaction is this map phi from the finite subsets, which is denoted by this P0, the finite subsets of the lattice, to the C-star algebra. This is localized. And each term is self-adjoint. Yeah. And we say it's bounded. So phi is bounded if the following expression is finite. X in supremum over all points on the lattice, and then I take the sum over all terms in the interaction that contain x. So if this quantity is finite. And its finite range if phi of lambda is equal to 0 whenever the diameter of lambda is greater than r. So this is the range. So I have equipped my lattice with a metric here. And I'm going to assume that the situation is nice enough, the metric is nice enough, such that the quantity nr, which is the size of balls of radius r, such that this quantity does not get too big. So this is the closed ball of radius r around a point of x. And I'm asking that with any such closed ball, the lattice points don't get too tightly packed together. Yeah, Robert. Yeah, that's what I'm doing. So this is lambda. This is a finite subset of the lattice. Right, yes. The sum is on lambda. Maybe I should write it like this. So this is lambda, which is a subset of gamma, such that x is in lambda. Okay. So that's the object I'm dealing with. And I remind you of the theorem that Bob showed at the end of his lecture. Which is that this thing defines, or that the local dynamics converge in the thermodynamic limit. Right, so we have tau lambda for a local dynamics, this was add of e to the it h lambda applied to A, where h lambda is equal to the sum over all interaction terms localized in lambda. OK, so maybe that's not the theorem yet. That's just the definition. And then the theorem is that for all A in A, the limit tau t of A over the finite volume dynamics, this converges and it converges uniformly on compact subsets.
When you define your lambda, you're using delta subset of lambda.
Yes? I'm summing over deltas. Should I write something else? Should I? Maybe I can write bigger. If I change from the notes, right? Oh, OK, Bob wrote Z. OK, that's good. I can write Z. OK. So let's compute the derivation. So first of all, if A is in the local algebra, in particular if A is in A lambda for some lambda which is a finite subset of gamma, then A is already in the domain of the derivation for any local operator. Right? We haven't yet said that the domain of the derivation is non-empty. It would be very bad if it was. But fortunately, it contains the local algebra, which is quite a large set. OK, so A is in the domain of the derivation. And we can evaluate the derivation explicitly. It's I, commutator with H, the local Hamiltonian, the closed ball of radius r around lambda applied to A. And what you should notice is that this is actually localized. This is in the local algebra, and it's in the ball of radius r around lambda. So this is in the local algebra. That's quite nice. So delta sends the local algebra to the local algebra. Yes, finite range. So let's do the proof. It's quite easy. Let's look at the derivative of tau t of A for finite lambda. This is I h lambda. Oops. This is actually tau at time t of h lambda of A. And you can compute that explicitly. Tau lambda is just conjugation by exponentials, and so you can just take a derivative of an exponential to compute this. All right. Now these derivatives, if lambda is large enough, so A is localized on some finite set, right? Let's say the domain of A is lambda here. But then if we take a ball, a much bigger ball, so here's B r of lambda, any interaction term that's not localized in this ball cannot reach the domain of lambda. So if I have an interaction term that's localized out here, it won't be able to reach the domain of A, and so it will commute with A. And so this quantity, I'll get to your question in a second, Daniel. This quantity will approach HBr lambda. Oh, OK. Maybe Daniel's going to complain that I have using lambda as a constant and as a variable. Is that what you're complaining about? OK, so all right. So it's OK here. It's not OK here. So this is, after a finite size, for z large enough, this will approach this. It'll stabilize. And so what you see then is that these derivatives also converge uniformly. And they converge uniformly to HBr lambda bar A. The limit is as z goes to gamma. And so now you know that the function converges uniformly and its derivatives converge uniformly. And so we can conclude the proof by your analysis 1 class. The limit of the derivatives is the derivative of the limit. Tau t of A is equal to I tau t of H Br lambda of A. And then we set t equals 0 to get delta of A. OK? Very good. So I can write this expression in more ways than one, which may be illuminating depending on how you want to think about it. But I could also write this as, you'll see this expression or I could have also written this as a sum over the interaction terms, right? The Hamiltonian is the sum over interaction terms. And so I could have written this as the sum over those terms that intersect the support of A, phi z of A. And there's finitely many such terms, so that's a finite sum. Awesome. All right. I can say even more. These local operators play especially nice with the derivation delta. Not only is tau t of A differentiable, it's analytic. OK? This is going to be useful in my next lecture. So I want to prove that for you, because the proof is fun. OK. Yeah.
Is d of delta and a loc, can you compare these algebras? Is one the subset of the other?
Yeah, this is saying, this theorem says that a loc is contained in d of delta. OK. fact, A loc is a dense subset of A, so in particular, it's a dense subset of D of delta. OK, so I said that tau T of A is analytic. So it has convergent Taylor series. And the derivatives are delta n of A. Right? The nth derivative, each time I take a derivative, I get a delta. And this has a radius of convergence for all 1 over 2 norm phi nr minus 1. OK, I don't know actually if that is the maximal radius of convergence, but it's a radius of convergence, and that's all I need. Yeah, Robert.
Delta n of A bounded operator.
Yes. So once I apply A, I land back in the quasi-local algebra. Well, I mean, it's an element of a C-star algebra. Okay? So delta n itself is not a bounded operator. Yeah. But delta n of A is an element of the quasi-local algebra. All right. Let's do the proof. Let's expand out this thing. We have this expression in terms of these sums of the interaction. And so if we have delta n, we're going to get n sums and n nested commutators. So this is going to look like, well, there's going to be a factor of I to the n. And then I'm going to have n sums. I'm going to have phi of zn, n nested commutators. I'll get phi of z1, a, like that. And these sums, so I do the sum over z1 first. It goes z1 up to zn. And the sum over z1 is over those z's that intersect lambda. But then as I go on, my support gets larger and larger and larger. And so I have to sum over more and more z's. So I'm going to write it like this. This is a sum zn. And I'm going to write this as lambda n minus 1. OK, so I'm going to define lambda naught here is defined to be lambda. And then lambda n is defined to, or lambda k, let me write it, is defined to be lambda. But then I have to union with z1 up to zk. All right. In order to show that this series converges, I need an estimate on this. So I'm going to take the norm. I'm going to do a huge triangle inequality, bring the norm inside all the sums. I'm going to bring the norm inside all the sums. And then I'm going to use this very simple estimate, which holds for all elements of the C-star algebra. This is less than or equal to 2 norm B, norm C. OK? So what I get at the end of the day is delta n of A is less than or equal to all these sums. This is sum of z1 intersect lambda 0, non-empty. This is z n intersect lambda n minus 1, which is not empty. And then I have a 2 to the n from this factor. And I have a norm phi z1 up to norm phi zn. And then I get one extra norm of A, because there's only one factor of A in here. OK. Now, I'm going to do these sums one at a time, starting with zn. And if I look at a general sum of this form, so let me say z tilde and lambda tilde, I can do another wild estimate on this. which is to vastly overcount. So if these things have a non-empty intersection, then there is some point x in lambda tilde which is contained in z tilde. So I can replace this by x in delta tilde. Right? So here I'm summing over x. Here I'm summing over delta tilde. So maybe that should be made more clear. So this is delta tilde, subset of gamma, such that x is in delta tilde. And then I put the norm phi delta tilde. So certainly everything I summed over here is also in this sum. But this inner term, I can now say this is the norm of phi. And that's just a constant. So this is the cardinality of lambda tilde times the norm of phi. So what I need is some estimates. I'm going to have now like lambda n minus 1, lambda n minus 2, all the way to lambda 0. I need some estimates on absolute value of lambda k, the cardinality of lambda k. Okay? Well, cardinality of lambda 0, this is just cardinality of lambda. Cardinality of lambda 1. Lambda 1 is by definition lambda union delta 1. And these have a point, these have a point in common. So this is less than this, minus 1, because they have a point in common. What? Oh, I knew that was going to happen. In my notes, they're all deltas. Okay. Right, and since I'm only considering those zn's which have a non-zero interaction term, this cardinality of z1 is bounded by nr. It's gone now, but this was the size of the ball of radius r. So this is less than absolute value of lambda plus nr minus 1. And if I do this, I can keep doing this, and you can show by an easy induction argument that the cardinality of lambda k is going to be the cardinality of lambda plus k times nr minus 1. OK, now I'm prepared to do this humongous sum. So I plug all these estimates in. For each phi of zn, I get a norm phi. And I get one of these factors. So I have delta n of a is less than or equal to. I have my 2 to the n. I have my norm phi to the n. I have one more factor of norm a. And then I have a product from k equals 0 to n minus 1 of the cardinality of lambda plus k times nr minus 1. And now the rest follows by the ratio test. OK, so that this series converges on this radius follows by the ratio test. And yeah, it's fine. I estimated z1 by nr. The minus 1 just came from the fact that they had a point in common. z1, if the cardinality is bigger than nr, then you will have a point in well, then the diameter of z1 is necessarily bigger than r, because the balls of radius r have nr elements. So if z1 has more than nr elements, it must have diameter greater than r. Okay. All right, my time is up. So we'll use all this or we'll use some of it in the next lecture. Yeah.
All right, any questions?
In your proof of that delta keeps the local algebra invariant, you use the fact that phi was finite range.
Yeah.
Can you give an example of a non-finite range interaction that doesn't, such that delta doesn't keep the local algebra invariant?
I don't know, maybe Bob can? Yeah.
If the interaction was exponentially decaying on, say, ZD, then the derivation is still well defined, but it doesn't take the local algebra to local observables anymore. So you could take any local observable, and the same calculation would work, but the object is not going to be a local sum anymore. You would be summing over all finite subsets that contain that support. For example, if it's supported at a single site, this sum here would be global because there could be all sorts of interactions that contain that site, but still finite in the sense that it's summable because of the norm on the interactions that you have. So you could make it relatively explicit, actually.
So in that final proof of analyticity, in fact, you proved complex analyticity, right, on a disk.
Yeah.
Could you also get analyticity in a strip in the complex plane?
I don't know. I haven't thought about it. Yeah. Okay. But yeah, Bob is probably going to be more capable of answering some of these
Can you
questions than
repeat the answer in the microphone?
Yes.
Any other questions?
I looked at Peter Niken's book.
This is going back a bit, similar to Ryan's question, but a common context in which you have many low energy states that are globally distinct are in spin glasses. And at the same time, I wouldn't want to call all those exponential or like extensive number of states different superselection sectors. So how would...
Could you say one more time? Sorry.
So how would this handle those where there are many low energy states that are globally that differ by extensive Hamming distance, for example, when you have randomness in the interaction terms?
And you say that these are not in different superselection sectors?
No, there's like an extensive number of low energy states.
I see.
You can consider like a Ising model with random coefficients taken from some Gaussian distribution, for example.
Okay, I'm sorry this is outside my realm of knowledge, but certainly you can have many C-star algebraic ground states in this sense. I don't know, maybe they would all be, or...
Because they are locally distinguishable by operators.
Yeah, that's fine.
Yeah.
You could have multiple C-star algebraic ground states in the same superselection sector. That would be possible.
Even though here they're not obtained from, like they still differ by global operators. So like in this, they're like globally different in the sense that Ryan was mentioning. Yes, but they are distinguishable, I guess. Okay. So in that sense, you would say it's like just an extensive number of superselection sectors?
That could be possible. Yeah.
Okay. I see.
Yeah. Right. Yeah. Unbounded below, or yeah.
Okay. Thank you.
One more. All right. Thanks, everyone. So the next will be at... Sorry. Does anybody know? You know when your talk starts. 10:10. All right. See you all then. 10:20. 10:20, everyone. Yeah. It's okay. It's not. I should have been more prepared.
I know, but it's